Okay, I think we're ready to start. Welcome everybody to today's event on the networking channel. The topic today is New Frontiers in Wireless Sensing. The event today is going Lili Cho. She is a professor in the computer science department at UT Austin. She serves as chair of ACM SIGMobile. She is a National Academy of Inventors Fellow, ACM Fellow, IEEE Fellow, and ACM Distinguished Scientist. She has won numerous awards, and she is somebody who is incredibly active in our community on organizing and program committees. And she is highly distinguished and known as, just in general, an incredible expert on wireless and mobile systems in general. So we're very lucky to have her here. She has brought together a set of other very highly accomplished researchers who will be on this panel as well, who you're going to meet shortly. Before we start, we want to mention the networking channel is a series of talks happening every 2 weeks. However, this is our final event for the season. We're going to be restarting after the summer ends on September 18th with an event that will be announced soon. With that, we're going to start the event for today. We would like to make this a very informal discussion. So to try and make it interactive, you can help us out by asking questions. There's a Q&A feature at the bottom of your screen. You can also enable closed captions if that's helpful for you to see what is being said transcribed in text on your screen. And there's also an option to translate the spoken words of these experts into other languages there as well. So with that, we'll turn things over to Lili. Yeah, thank you, Lili.
Thank you, Matt, for a kind introduction, and thank everyone for joining. I'm so delighted to have a group of fantastic researchers to share the cutting-edge research on wireless sensing. For the audience, welcome to type your questions in the chat. And today we have a fantastic program. We'll start with Joerg Widmer, who will present joint communication and sensing with unsynchronized transceivers. Then Professor Xiong is going to share his exciting new research on new sensing modality, quantum wireless sensing and leakage wireless sensing. Then Haitham, Qian, and Fadel will talk about a very exciting application for wireless sensing, ranging from self-driving cars to understanding human behavior to sensing climates, robotics, and smart environments. Last but not least, Professor Swarum Kumar will share his cutting-edge research from wireless sensing to wireless actuation. Without further ado, let's start with Professor Joerg Widmer. He is going to talk about joint communication and sensing with an unsynchronized transceiver. Joerg is a research director and research professor at IMDEA Networks in Madrid, Spain. His research focuses on wireless networking, ranging from extremely high-frequency millimeter wave communication and MAC layer design to mobile network architecture. Joerg authored more than 200 conference and journal papers and 3 IETF IFC and holds 14 patents. He served on the editorial board of IEEE Transaction on Mobile Computing and Computer Networks and Program Committee of various major conferences. He has 13 Best Paper Awards. He is Fellow of IEEE and a distinguished member of ACM. Let's welcome Joerg.
Thank you so much for inviting me. And for the very kind introduction. I'll be talking about joint communication and sensing with unsynchronized transceivers. It's a topic that currently is quite hot, quite up and coming. Of course, synchronization and sensing with wireless hardware has been going on for a long time, but there's renewed interest in the topic specifically because now new communication standards are so much more powerful that you achieve accuracies that make this wireless sensing with communication hardware suitable for many application scenarios, which before was very difficult. And due to that, there's a lot of interest also from industry and standardization at the moment. Now, I'll specifically look at millimeter wave JCAS systems, because that's also the research area that I focus on. And these systems are specifically interesting because of the very high bandwidth you have at millimeter wave. And this very high bandwidth gives you very good ranging accuracy for localization and sensing. And at the same time, you have highly directional antenna arrays with many antenna elements, which give you very good angle resolution. And those two together, good range resolution, good angle resolution, allow for highly accurate multipath decomposition. And that is useful, of course, for active localization, because then if you can separate the different paths with respect to their delays and angle of departure and angle of arrival, you can remove indirect paths from the direct line of sight path that you want to use for active localization. Or if you're interested in passive localization, right, you have a person, a reflection off of a certain person, and you'd see how that multipath reflection changes over time to track where a person is walking. Or you might want to have even more information, for example, extract microdoppler that's introduced on that path that's coming off of the reflection of a person to understand more about, like, for example, the activities that that person might be doing. And you want to do that in a multi-static setting. So typical radars are monostatic. They require full duplex operation, and that's just incompatible with current communication networks, right? So you'd much rather have this multi-static between a base station and smartphones, for example. And one big advantage, besides being compatible with current networks, is that you have many different links available, right? Sort of a monostatic radar sees one view of the object. But if you have many base stations, many smartphones communicating and sensing the environment, obviously you see an object under many more angles and from many more viewpoints. Now, the big issue with this, and that's been a problem for all the past decades where sort of people look at sensing with wireless hardware, is that the nodes are unsynchronized, right? Sort of the clocks of the transmitter and of the receiver are independent, and you have things like frequency offsets, carrier frequency offsets, and timing offsets due to that. Now, for active and passive localization, that's not so much of an issue. You don't care so much about the frequency offsets, and timing offsets are easy to compensate for. So that's something that's very manageable. Now, at the same time, there's been a lot of interesting work at sub-6 gigahertz MIMO for sensing, for example, respiration monitoring. And there also you have very clever ways to take care of the frequency offsets, phase offsets between transmitter and receiver. One approach, also Joerg, who's going to talk later, has been working on that for respiration monitoring, is, for example, cross-antenna based timing offset and CFO compensation. And the idea is basically whatever offsets you have, they affect all of the receive antennas. So if you divide the phase, or if you divide the CSI from one antenna of that of another antenna, those phase offsets basically just cancel out. And what remains is sort of the difference in the signal phase differences in the signal that are introduced by the channel, so the object that you want to sense. Now, the big issue with that is that this doesn't usually work in millimeter wave systems, right? So typically millimeter wave systems, or at least the current ones, only have a single RF chain. They're not MIMO systems. You cannot look at phase or CSI at specific antenna elements. You only have a single RF chain behind one phased array, and that's all you see. So then if you did something, for example, like microdoppler extraction, you have a transmitter, receiver, you look at the path reflected off of objects, but together with the frequency and the timing offsets, you basically don't see anything at all. The problem is that these offsets, for example, CFO offsets with current millimeter wave systems, they're 2 to 3 orders of magnitude larger than the microdoppler that you actually want to observe. And then obviously without compensating for that, you cannot use such systems directly for example, sensing to extract microdoppler. Now, how can we deal with that? One way to do timing offset compensation is by looking at the channel impulse response. Now, that is something that's relatively straightforward. If you have a line of sight path, right, you just look at when that line of sight path arrives, and that gives you sort of a timing reference. As long as the line of sight path is there, then everything else is just relative to the arrival of that line of sight path. Now, the problem is with millimeter wave that you have few paths, and of course there's blockage. So that line of sight path might go away, and then you have a big problem if the line of sight path suddenly is blocked, and the first path that arrives is from a reflection. Suddenly your whole timing offset jumps. So you can't have that. Now, there's a way around that, and that's actually very nice because at millimeter wave, you have such a good timing accuracy. You can cross-correlate the channel impulse responses of the different packets over time. So here, for example, what you would have is one strong peak that is, for example, the line of sight path in one channel impulse response. And then later on, you have a reflection. And then afterwards, you get another packet. Again, the line of sight peak looks a bit different. The other reflection peak, you do a cross correlation between those. And of course, you get directly the timing offset that allows you to align those packets. Now, the nice thing is that if the multipath environment changes, for example, the channel impulse response of the line of sight path quickly becomes weaker, but the rest of the multipath environment stays the same because only the line of sight path is currently being blocked, that cross correlation still works. And basically that allows you to sort of estimate timing offsets, even if the multipath environment changes quite a bit. Now, once you have this, once you have timing alignment, you can take care of these timing offsets. You can basically look at the different multipath components. And that's how we take care of carrier frequency offset compensation. And the idea is as follows. So the problem is estimating the carrier frequency offset is not really feasible in a way that's accurate enough, just because it's so much larger, so many orders of magnitude higher than the Doppler that you want to observe. But what you can do is you can look at static paths versus dynamic paths, right? So for example, here, you might have a static path that's reflected off of a wall. And of course, then there is no Doppler, right? There's only the carrier frequency offset in that path. And now, since millimeter wave gives you such good multipath resolution, you can basically extract the signal of that path in isolation. You get another path, that's the one that you're actually interested in, which is the one reflected of objects that have the Doppler and the same offset in terms of carrier frequency offset. You do conjugate multiplication, the carrier frequency offset gets removed, and what remains is the Doppler itself. And that's one way to actually take care of the carrier frequency offset without having to estimate it, and that's very important. So that's one way of doing sensing, unsynchronized millimeter wave transceivers, even if you only have a single RF chain. And here, just a very quick example that this actually works. On the left is an example where you have a full system phase locked and synchronized. On the right is a system we experiment with where everything is unsynchronized. We do this kind of compensation, and we have intermittent non-line of sight, right? And you see that even when the line of sight path is blocked and reappears, this works. So even in very complex settings, many people in the same room at the same time, you do activity recognition, this still works. So thanks a lot. With that, I conclude my talk.
Thank you so much, Joerg. And next we will have Professor Xiong. Jie is a principal researcher at Microsoft Research Asia Shanghai Lab. I had the pleasure to have Jie as my colleague. He is also an associate professor at UMass. He received his PhD degree from Department of Computer Science, University College London in 2015, supported by Google European Doctor Fellowship. His research is supported by NSF Career Award and NIH R01. He has broad interest in wireless sensing, smart IoT, cyber physical systems, mobile computing, and wireless networking. He won NSF Career Award and many Best Paper Awards, including Census's MobileCom Best Community Award, CCOM, and CONEX. Now let me turn over to Jie.
Okay, sorry, Lili. I think I have some issue with the sharing. Give me like 1 minute.
No worry.
So can you see the screen? The full...
Yeah.
Okay.
Looks good.
Okay.
Yeah.
Okay. Yeah. Thank you for the nice introduction. So today I'm going to introduce two pieces of my recent work, which are quantum wireless sensing and leakage wireless sensing. So in the last 10 years, so we have seen so many different types of wireless signals being utilized for sensing purposes, Wi-Fi, LTE, LoRa, UWB, and acoustic signals. So while promising, we still find there are some issues associated with existing wireless sensing. So I just listed 2 here. So the first issue is for one particular signal, actually the sensing granularity is still limited by the frequency, by the bandwidth. So take the Wi-Fi as one example. Wi-Fi sensing is capable of sensing respiration, but it's not able to sense heartbeat. Another problem is like more general. So for current wireless sensing to work, normally like dedicated transmissions dedicated signals needs to be transmitted. Also take Wi-Fi as one example. For Wi-Fi sensing, we need to transmit at least 100 packets per second. So this will affect the ongoing Wi-Fi communication. So in these 2 new sensing modalities, which the first one is a quantum wireless sensing, we targeted to significantly improve the sensing granularity. And for the second new sensing modality, leakage-based sensing, we aim to remove the dedicated transmission and use the ambient transmission for sensing purposes. So I will briefly introduce a quantum wireless sensing, and for the second one, I'm not sure if I have time, but I will try. Okay, so first, quantum wireless sensing. So before I give you more details, let me present a little bit the basics of the basic factors limiting the sensing granularity. So for traditional RF transmitter and receiver, actually the hardware thermal noise is a key factor. The key factor limiting the signal to noise ratio. So we can see from the right-hand side. So if there's no noise, the signal is ideal, it's very clean, it's very smooth. But with the hardware noise, actually what we received at the receiver side is affected by the noise, and the signal pattern caused by the target motion is not clear. So in this quantum sensing, actually we involve the quantum receiver. We replace the traditional RF receiver with this quantum receiver for the first time to realize quantum wireless sensing. So the basic idea behind quantum sensing is that we need to understand what is an atom. So all the matters in our world is composed of atoms. And these atoms, the basic structure is a nucleus and also electrons located at different orbits level. So we can see here, the orbit has a index n equal to 1, n equal to 2, and n equal to m. So this m can be as large as 50 or even 100. So another very interesting property is this atom is actually capable of absorbing signal or transmitting signal. So if this atom absorb one signal, actually absorb some kind of energy, the electron will jump to a higher orbit level. And on the other hand, if the electron of the atom will transit from a higher level to a lower level, actually this atom will transmit signal. Of course, during this transition process, the signal frequency actually depends on the 2 levels. So which level you are transiting from and which level you are transitioning to. So another question is how to make sure this atom is capable of transmitting or absorbing signal. We need to use a laser to trigger this atom to a new state called a Rydberg state. And once one atom reaches this Rydberg state, it's called Rydberg atom. So what is the definition of a Rydberg atom? So for an atom to be called a Rydberg atom, at least one electron needs to be triggered to a very high level. This high level we divided with an index larger than 20, which means at least one electron is triggered to a level higher than 20, orbits level higher than 20. Okay, so for electrons at different orbits level, actually we are able to calculate the energy level of this electron. So we are able to calculate if I want to receive Wi-Fi signal, I need to trigger the electron to which level. I give 2 sample calculation here. So if I want this atom to receive Wi-Fi signal, Wi-Fi waveform. So I will need to use a laser to trigger the electron of the atom to level 66. And once this atom receives some Wi-Fi signal, the electron will be triggered to another higher level, which is a 67 level. And of course, I can change the level to receive other different type of signals. If I want to receive a signal at the frequency of 28 gigahertz, I will use a laser to trigger the electron to 61 orbit level. Okay, so with this, I introduce a basic basic principle behind quantum receiver and quantum wireless sensing. So for wireless sensing, we care about the signal variation. We use a signal amplitude variation. We use a signal phase variation to monitor, to infer the target's motion information. So how to measure the signal, how to measure the signal variation, the signal amplitude variation, how to measure the signal phase variation at the quantum receiver side. So we capture the signal amplitude or phase variation using the spectrum of the trigger laser. So the spectrum of the trigger laser has one peak when there's no IF signal coming. So when one IF signal is received, the peak actually is split into two. And if the signal is stronger, we find the peak separation is larger. So by measuring this like peak separation, we can very accurately know, okay, what is a signal amplitude level. So here I show the experiment setup. The first state is the cesium atom at the ground state is not triggered by the laser. And the second one is cesium atoms triggered by the laser to the readable state, which is able to capture like IF signal, IF transmissions. And the last one is our setup. And here, so we compare the sensing capability of quantum wireless sensing with the traditional IF sensing. So we use three different hardware for traditional IF sensing, which is a USRP, LIM-SDR, and a commodity Intel 5300, which is a Wi-Fi receiver. So what I show here is the waveform we received, we captured at the quantum receiver, and we captured at other like conventional IF receiver. We can see the first row is the signal waveform we captured at the quantum receiver. It's very obvious. The signal, the waveform captured by the quantum receiver is much cleaner than the other three. And because of this, we can enhance the sensing granularity by around 5 to 10 times based on our measurements. So for Wi-Fi sensing, the traditional like IF receiver will able to monitor vibration at the amplitude which is like larger than say a few millimeter. But with this quantum receiver and the same Wi-Fi transmitter, we are able to improve the granularity to 0.5 millimeter. And we tested at a different frequency band, like Wi-Fi band and 5 gigahertz, both 5 gigahertz and 2.4 gigahertz for Wi-Fi, and 28 gigahertz for millimeter wave. Okay, so now let me briefly introduce the second topic, which is the leakage-based sensing. So we ask this question: can we utilize ambient, non-dedicated signals for sensing? So we find there are actually like leakage IF signals in our surrounding environment. So what I show here is a power line leakage. So we have a lot of leakage as long as we have power lines in our building. So after we dig deep to utilize this power line leakage for sensing, we realize it's quite different from traditional like IF sensing, such as Wi-Fi sensing and the millimeter wave sensing. This is because like a Wi-Fi signal, actually the frequency, the carrier frequency is like 2.4 gigahertz, 5 gigahertz. But for this leakage, it's only like 60 hertz, which is very small, much smaller. So for the traditional like IF wireless sensing, the signal is actually reflected from our body. We then capture the signal and analyze the signal variation to tell, okay, what is the motion. But here, once we use a leakage signal for sensing, it's very different. So actually for this leakage sensing, we treat the human as an antenna, because now actually the human body is not able to like affect the signal in terms like signal amplitude or phase. What we are doing here is actually the human now is serving as an antenna, and because the antenna is changing, when the human is like performing one gesture or one activity, the antenna is changing. Because the human antenna is changing, then the signal is varied. So this is two very different like sensing modality. And we also utilize the second one to do something similar to the first one, although the sensing granularity is not as high as like Wi-Fi or like millimeter wave sensing. But we successfully like demonstrate it's possible to use like a very low frequency leakage for sensing purposes. So what is more interesting is we find this leakage is not just like from power line. We also find the leakage from the from other sources. So one very nice example is from the EV, the electric vehicles. So we also successfully utilize this type of leakage from the car for like sensing the driver's information. So with that, I will just like summarize my talk. So I think just one takeaway. So we have achieved promising progress in wireless sensing in the last few years, but I believe like exciting new sensing modalities are still there for our to discover. Thank you.
Thank you, Jay, for your exciting talk. Next, we'll have Fadel. He is an associate professor at MIT Media Lab and ECS. His research has led to multiple startups. He's currently CEO and co-founder of Cartesian System, a startup that aims to sense the physical world at an unprecedented scale and precision. Prior to that, his PhD research on wireless sensing, which won ACM SIG Mobile Dissertation Award, led to Emerald Innovation, whose devices are used for remote health monitoring for thousands of patients. He has received various awards, including one of the world's top 35 innovators under 35, a young global leader by the World Economic Forum, and the ACM SIG Mobile Rockstar Award. He presented his research to President Obama at White House. And here are three interesting numbers: 50, 103, and 25 million. Guess what these numbers are? 50 is his research has won one of the 50 ways MIT has transformed computer science. And 103 is one of the 103 ways MIT is making a better world. His research is considered at that. And 25 million is his video has reached over 25 million people. So let's welcome Fadel to share his research on wireless sensing for new application, climate, robotics, and smart environments.
Thank you so much, Lili, for your kind introduction. And I will make sure to keep it under 8 minutes, but if not, please feel free to stop me so that I make sure I leave time for everybody else. Hello, everyone. Thank you for joining us. Today, I want to talk about, give a glimpse of what we're doing on decoding hidden worlds using wireless sensing. And this goes back to the motivation of the research and work that I do. I am interested in being able to decode or uncover parts of the world that are otherwise hidden from us. Because I want to be able to see and sense things that are difficult to reach and that are hidden from us. And this desire has driven my research going back to what we started about 12, 13 years ago on using Wi-Fi for sensing, in a paper that I published with my PhD advisor at the time, Dina Katabi, on how we can see through walls with Wi-Fi. So using wireless beyond traditional applications with the goal of decoding hidden worlds. And this has driven my research over the past 12 years. And today I'm fortunate to do this in two contexts, both in my lab at MIT and in my startup Cartesian that spun out of my lab. Broadly, what we do is we develop new technologies, new sensing technologies for decoding hidden worlds. And we do this in three main approaches: by batteryless sensors, wireless perception, and robotics. And we apply these technologies to solve problems in a wide variety of areas, ranging from oceans, climate, health, and ecology, to indoor logistics, drones, and augmented reality. Now, of course, in the interest of time, I won't be able to get into all of these. And today, instead, I want to focus on one area of research that I'm very excited about. To motivate it, I want to share a question that I asked myself when I started as a faculty. And that question is, what plays the largest role in the world's climate? Is it carbon dioxide, agriculture, transportation, buildings? Actually, it's the ocean that plays the largest role in the world's climate. It mediates our weather and it impacts our entire climate system. And it is also the part of our world that has been most impacted by climate change over the past 2 decades. In fact, the ocean over the past 2 decades has absorbed over 90% of the excess heat content that we've emitted into the atmosphere. Today, it holds more than 93% of CO2 on the planet. With the ocean playing such a big role in climate and being impacted by climate change, you might ask, how much of the ocean have we measured? Or if I were to ask this question differently, what percent of this ocean, of our ocean, have we never observed? Turns out it's a pretty large percent, over 95%. And that's a big problem because it also means that we don't know in what way, for example, climate change is impacting the vast majority of our ocean, and by that, the vast majority of our planet. So coming from a networking and sensing background, I started to think about how we can observe the ocean. And what I wanted to do along with my lab is think about how we can build an Internet of Things to observe the underwater world, build sensors and deploy them at scale and use them for monitoring the pulse of the planet or the pulse of the ocean. As we try to do that, to take sensors and deploy them, we faced a problem. And the problem was that the battery life of underwater sensors is extremely limited. When we looked more into this problem, we realized that it's actually fundamentally a communication and networking problem. And the reason is, what drains the sensor's batteries is that even low power underwater transmissions consume few watts. They cannot be recharged easily. If you have a sensor that is in the ocean and you want to recharge its battery, you need to send a ship, spend $50,000 to $70,000 a day just to replace its battery and come back. This is why today, most state-of-the-art sensors for continuously tracking marine animals or marine habitats can only last for a few hours or days, after which their batteries die. And this makes it very difficult to use them for long-term underwater observations, tracking migration patterns, underwater climate change monitoring, and so on. And it got us to think about ways that we can reduce the energy consumption of underwater communications and underwater networking. To do that, we invented the technology that enables underwater backscatter networking. This type of networking technology is so low power that it can communicate entirely using harvested energy without requiring batteries. I want to briefly describe how underwater networking works, underwater backscatter networking works, by comparing it to traditional underwater communication. In these environments, you typically have an underwater drone, and it wants to communicate with a large number of sensors. For simplicity, let's consider one sensor. For those of you who are not familiar, you cannot use Wi-Fi or Bluetooth underwater because they use radio signals which die exponentially fast in water. Instead, use sound. So the sensor has a speaker, the underwater drone has a hydrophone, and you encode your data using sound and you transmit it. The problem with this approach is that it consumes a lot of power and that drains the sensor's battery. In contrast, with our technology, both the speaker and the hydrophone or underwater microphone are on the drone. And the sensor simply has a reflector, which you can think of as a mirror. Now, when the speaker transmits sound, it reflects off its reflector and it comes back. And now if I want to encode information, all the sensor needs to do is to switch its reflector between reflective and not reflective state. So in contrast to the traditional approach where the sensor generates its own acoustic signal and that drains its battery, using our technology, you communicate by simply reflecting existing acoustic signals, and you can do that at extremely low power. Now you might be wondering, what did you do? You just moved all the energy consumption from the sensor to the drone. And the answer is yes, but that's exactly what I wanted to do, because the drone has its own power source, or you can imagine an access point on a ship or near the shore, and now I can scale this to a large number of sensors that are batteryless and deployed in the ocean. And of course, what I want to say here is that the acoustic reflector, which is a mirror, this is just an analogy. In reality, what we use is we use piezoelectric materials, and we figured out a way that we can modulate the sonar cross-section of a piezoelectric material. We built very many different sensors. This is one of the ones that you can see. Our sensors are omnidirectional, so they can reflect the signal back in all directions or retro-reflect it back in the direction that is desired. So you don't need to know where the mirror needs to send its data back. We also showed that it consumes 1 million times lower power than state-of-the-art low-power modems. And over the past few years, we've extended the technology in different ways, developing new node designs, developing communication theory and methods, showing how you can use it for underwater localization, because similar to how Wi-Fi does not work underwater, also GPS does not work underwater. And so we use our sensor to enable underwater GPS. How we can bring tiny ML or low power AI to these batteryless underwater sensors and enable long-term monitoring. And there we developed the world's first battery-free underwater camera. And finally, we also, this is, as I mentioned, we built the first underwater camera. This technology has applications both in the oceans on our planet and in the oceans of extraterrestrial planets such as Saturn's moon Enceladus and Jupiter's moon Europa. And we've been working with astronomers so that we can incorporate our technologies as part of future space missions so that we can search for life in extraterrestrial planets in our solar system. With this, I will wrap up. Thank you very much for listening, and I'll move on back to Lili. Thank you.
Thank you, Fadel, for your wonderful talk. And next we'll have Haitham. Haitham is an associate professor at EPFL. His research is on wireless networking, mobile systems, sensing, and algorithms. Before joining EPFL, he was a professor at UIUC. He received his PhD and master degree in ECS from MIT in 2016 and 2011, respectively. His PhD thesis on the sparse Fourier transform won the ACM Doctor Dissertation Award for the computer science thesis in the world, and the Best Thesis Award at MIT and TR10 Award for the top 10 breakthrough technology in 2012. His research has received Best Paper Award at ACM SIGCOMM, MobileSys. He is also a recipient of NSF Career Award, Google Faculty Research Award, and Sloan Fellowship. Now let's welcome Haitham, who is going to share with us his exciting research on high-resolution millimeter wave imaging for self-driving cars.
Okay, thank you, Lili, for the kind introduction, and thanks for everyone for being here. So today I'm going to tell you a bit about our work kind of using wireless signals for self-driving cars. And as you know, there's a lot of interest in kind of...
the screen sharing seems not complete. It only occupies a small window.
We see the presenter view.
Oh, okay. No problem. Do you see... Is it better now?
And
okay.
then, yeah,
okay.
That's perfect.
Thank you. Thank you. Okay, thanks, Swarum. Okay. So as you know, there's a lot of interest in self-driving cars and getting self-driving work. A lot of companies and startups are working on this, but at the same time, we still see that kind of these vehicles just cannot work in bad weather. They cannot work in snow, fog, storms. And basically, it's very well kind of established that if you want to kind of have self-driving cars, they need to work in bad weather, because like most places have bad weather. Unless you're in sunny California, you will not have good weather all year long, right? So the question is how to get them to work. So just let me start by showing you a vehicle, example of a Tesla driving in clear weather. And you can see the dashboard, and it kind of shows everything works fine. It kind of detects the cars that are passing by. It has no problem whatsoever. But the moment we switch to kind of, there's a little bit of fog, it either aborts, it says I don't drive, you take over, or worse, it continues to drive, but it doesn't detect. You can see the cars passing by, but it doesn't detect them. And so that you don't think I just picked this one example where it didn't work, here's another example showing that it just doesn't work in fog. It kind of doesn't detect the cars passing by. And the reason for this is basically most self-driving cars like Tesla, Waymo, and most kind of the ones on the market mainly rely on LiDAR and cameras, which are kind of optical sensors. They rely on optics for kind of imaging the environment. And these don't work well in fog, in sandstorms, in blizzards. Cameras don't work well in low lighting conditions. So they fail in these cases and they don't work. And this is what brings us to kind of wireless sensing and specific millimeter wave radars that can penetrate through fog. They can penetrate through kind of sandstorm, work in low light, doesn't matter. And so today cars do have radars, but the radars are used just for ranging. They can tell you how far the car in front of you is, what its speed, but they don't give you much more information. And our goal is to get a lot more information from the radars. However, the problem with radars is that their resolution is low. So this is an example of an imaging of a car using kind of a radar. You can see the point cloud and the top view, front view. And as you kind of notice is that if I don't tell you car, you might not even know it's a car. But if I show you the silhouette, you start to see that, oh, this is the side of the car, this is the front of the car. But kind of it's the resolution, it's much kind of worse than the camera. The resolution is very low. You mostly see blobs. There's no sharp edges. There's specularity, which means that parts of the signal, the wireless signal goes to the car, bounces off, completely different direction. You get a missed piece of the car, so now you don't get the full, and then you get a lot of kind of artifacts due to multipath reflections. And so when we started working on this problem, we were hoping kind of with algorithms and we would be able to get higher resolution, but kind of we failed and quickly realized that there's no way to fix kind of these specularity problems without kind of machine learning, without a data-driven approach, basically relying on the fact that kind of we know how a car looks like. And so I'll talk about kind of two applications. The first is bounding box detection. Can we tell kind of where the car is exactly kind of bounded by a box, have very accurate kind of bounding box detection. And the first thing we noticed is that because radars, especially the commercial ones, use multiple transmitters, as the car moves, these transmitters take turns transmitting. So the scene is not static, and we don't know how the car is moving. And if you try to image, you get kind of a smearing of the signal. Now, we did devise kind of algorithms to correct for that smearing, but it doesn't kind of always kind of work in all scenarios. But at the same time, we realize that, okay, if we take a low resolution using, for example, one radar transmitter, we get a much lower resolution image, but then it doesn't have this smearing effects because it takes just one snapshot. And so what we kind of realized that for this to work really well, the machine learning model, if you feed it both the high resolution and the low resolution radar heat maps, it kind of can perform much better. So basically, what we do is this is kind of a detection network, and you feed it both in parallel, both a low resolution version of the radar, high resolution version, and then you concatenate them, and it goes to something called a feature pyramid network, extracts the features. You also do a polar to Cartesian conversion, and then you can kind of detect the bounding box. Let me show you kind of some results of this. So this is kind of the green is the ground truth, the red is what we predict. And if you compare this to kind of just giving it the input, the radar heat map itself, without kind of correcting for the smearing and without kind of using the low and high resolution, you end up kind of a lot of mistakes. So here, quick demo video. Now in this video, it's just detecting frame by frame. So it's not doing temporal post-processing. So you're going to see in some cases a car disappears, then it shows up. So this is because we're not taking time. So if you incorporate time into this, you can smooth out the errors that kind of it makes. But you can see that it can kind of detect the cars quite well as they turn around. And this is just using radar, so it's not on the cameras or anything. We have kind of, I'll show you a bit later, even if there's fog, it kind of works equally well. Even if you cannot see anything, it can detect exactly where the cars are. Okay, so this is kind of one thing. One important problem with all this work is that it is very hard to label the data. So if I give you for machine learning, you need a lot of ground truth, and basically if I give you this radar heat map and tell you where's the ground truth, it's very hard to do it. And you end up kind of having to do it manually, and even for experts, it's actually quite difficult. And so what ends up happening is you have this huge amount of data that you cannot use for training because it's not labeled. So just to label 3,000 frames, it took us like a couple of months. So the question is, can we use all this unlabeled data? And for that, kind of, there's a technique called self-supervised learning. And the idea at a high level is that rather than kind of have the ground truth, you try to kind of extract features from vision rather than extracting the ground truth, which doesn't work well, and as well extract features from augmented versions of the same radar data. So for example, I can take a radar image that I know how it is. I can, for example, rotate it, crop it. These are popular techniques in computer vision, but in radar, you can do more. You can have random phase noise. You can remove some of the transmitter antennas, some of the receivers, create a much larger data set where you can know what the ground truth is. And what we show is with that, you can even, so the first system I showed you was called Radatron. This is called Radical. You can even do much better. And in the last kind of 30 seconds, their application is kind of, can you extend this beyond kind of just bounding boxes to do a full-fledged 3D imaging? But as I showed you, kind of, it's actually difficult because the resolution is so low. And this is, again, where kind of machine learning comes in, and specifically is leveraging geometric priors in the sense that a car looks like a car. There's a kind of limited shapes that a car can look like. Bikes, humans, everything you see on the road is not random. And you can use machine learning techniques like GANs, which what we used in the project, to actually get much better imaging results. And so, but again, there's not enough data. So in this case, we trained on simulated data and tested with real data. So we used kind of CAD models of cars. We simulated how they will look like in 3D heat map, and you use that for training. And so this is some results. So the ground truth is a 2D heat map, depth map. And then use a fog machine to simulate very dense fog. The camera completely fails, but the radar kind of can capture the reflections, and you can use machine learning kind of to map it back to its original shape based on kind of the point clouds you get from the radar. And as I said, this is only, you can do this by training with simulated data. So I will wrap this up. I think millimeter wave kind of sensing is going to be very crucial for self-driving cars to get them work kind of in bad weather conditions. The code for these projects is online, as well as the data set. So feel free to kind of try it out. Thank you.
Thank you so much, Haitham, for your very interesting talk. Next, we'll have Qian. Qian Zhang joined the Hong Kong University of Science and Technology in 2005, where she is now Haitham Professor of Engineering and Chair Professor. She is now serving as the acting head of Division of Integrative System and Design. She is also serving as the director of Digital Life Research Center and the director of Microsoft Research Asia Information Technology Key Laboratory. Before that, she was in Microsoft Research Asia from July 1999, where she was a research manager of the Wireless and Networking Group. Dr. Zhang has published more than 400 refereed papers. She is a fellow of the IEEE and a fellow of Hong Kong Academy of Engineering Science. Today, she will share with us understanding human behavior with wireless sensing.
Thank you, Lili. Thank you for inviting me, and it's very happy to be here. So as Lili asked me to talking a little bit about the sensing for healthcare, so today I want to bring like a very, very brief idea about what we are doing now for the sensing for healthcare. But considering the time is very limited, I will try to speed up and hopefully I can finish in 5 to 6 minutes. Yeah, so pretty much the context setting in this panel, we are all doing different type of sensing. So there are various type of sensing modalities, particularly from the wearables to contact-based opticals, and then even to the contactless ones. We are all talking about RF, acoustic, light-based sensing, etc. So to me, the most exciting part is related to those contactless sensing capability because that's very, very essential for healthcare applications. So we can see that especially for the home-based healthcare, a lot of people are suffer from chronic disease. So how AIoT can eventually help? So we can see that with sensing capability, we'll be able to understand the typical vital sign indicator like the blood pressure, breath condition, etc. And then also the health-related lifestyle behavior. For example, whether there's a gait change, whether there's like a eye blinking pattern change, etc., etc. So with these two types of information putting together and working together with the doctors, we'll be able, for some disease, we have the digital biomarkers so as we can find out disease earlier. And most of the cases for the chronic disease one will be able to do the assessment of the disease progression level. Not only that, we'll be able to provide personalized like intervention in the way that give you a suggestion about the rehab, exercise, breath, exercise, etc. How effective that is? Well, we have the very nature closed loop because we can do sensing, we can do the analysis again. So that's why in HKUST, we are particularly focused on this application about the healthcare. And technology-wise, we are actually playing with different type of sensing modality. And not only the sensing modality, but we also leveraging the development of the machine learning, especially for the edge AI side, because now we have the resource-constrained edge device need to make the decision in a reasonably real-time manner. So with this, we actually are working on different type of diseases under the home setup. So I just want to use a very quick example to demonstrate the nature of those type of work. So let me just choose the respiratory disease as an example. And COPD is one of the very common lung disease. And so that's why if we are really be able to have a good care for COPD patient, we should do frequent non-functional assessment. And moreover, basing on those non-functional assessment, we should do the proper personalized breath exercise recommendation. So if you are asking people to do non-function assessment, normally if you go to the hospital, that's the standard solution will be the expensive respiratory test. You do the maximal effort breathing with the inhale, exhale phase. So eventually you got this flow volume curve. But go to the hospital to do this assessment is just too inconvenient. So can we just leverage the microphone in your earphone so as to be able to enable this mobile respiratory concept The answer is yes, in the way that the key observation is if we want to get a flow rate, we're trying to understand the airflow speed. We find out physically actually is highly related to the airflow sound, which we perfectly can leverage the microphone to capture it. Again, those are the technical details. I will just skip it. But the fundamental is by very detailed understanding the physical meaning of the acoustic information, we do feature extraction and then phase segmentation. And then we define the deep learning-based model to do the regression for the flow volume curve. So that just using such an earphone will be able to get a professional device-related, similar compatible performance. So after you have the assessment, what should you do? You will do the exercise. But when you do the exercise, your therapist will tell you that you should do like frequent diaphragmatic breathing at home. But how can I know whether I do it correct or not? Nobody give me a right feedback, and it's very hard for me to persist on this exercise. So for that part, acoustic sensing helps. So we have the smart speaker can emit the ultrasonic, and then we have the microphone array, which will be able to capture the information. But as we definitely know that the breath type is much difficult to capture comparing with the breath rate. So with this, again, you need a physical signal processing side do a lot of job in terms of detect the breath phase, and eventually a proper machine learning model will be designed so as you get a type related information. So we'll do this not only for the acoustic related monitoring, we can also leverage our millimeter wave to do the home-based monitoring. Dry eye detection is one example. So the reason is we have the dry eye because we have lost the stableness of our tear field. So we work with the hospital doctors, and then we find out the very interesting thing is if we can measure the spontaneous blinking, there's some nice characteristic in terms of incomplete blink, short blink interval, prolonged eyelid close time, etc. So all those are very unique characteristic, which gives us the opportunity. We can do the millimeter wave-based sensing. So we design a series of chips, and then we will have the frame chip variance calculation. And out of that, we can extract the biomarker of the dry eye disease. And then we design the deep learning model. We're using the unsupervised domain adaptation model so as to get a reasonable accuracy result. So just give you a high level ideas, we collaborate with hospital, with the doctors, and then we collect 54 participants, and then the accuracy in terms of the dry eye disease screening actually could be extremely high. Just using this slide as my last slide, I think there are a lot of exciting opportunities, especially there are more enhanced sensing modality like the metal surface, rays, even the fabric as a sensing modality. And there are a lot of advance in terms of the AI model, how to adopt a large model to the edge side or even to the tiny resource limited device. There are a lot of interesting discussion. More importantly, looking at the application. So we really be able to leverage those to enable the digital therapy to improve our health. So with this, I will stop here.
Thank you, Qian, for your very cool talk. And next, we'll have Swarum. Swarum Kumar is an associate professor at CMU ECE department with affiliate appointment in CS and HCI and Cyber Security and Privacy Institute. He designs and builds novel systems to enable faster wireless networking and a new service. Swarum is a recipient of this year's ACM SIG Mobile Rockstar Award and the 2021 ACM SIGBED Early Career Research Award and the NSF Career Award and Google Faculty Research Award. Swarum received the Best Dissertation Award in Computer Science at MIT and the president of Indian Gold Medal at IIT Madrid. And today, Swarum will talk about from wireless sensing to wireless actuation.
Thank you so much, Lili. Hopefully you all see my slides correctly.
Yeah, it looks perfect.
Okay, good, perfect. So thank you so much, Lili, for the invitation, and it's wonderful to speak to all of you and hear about all the cool work going on in wireless sensing. So just to make things interesting, my talk today is going to be a little bit contrarian and advocate something called wireless actuation. We should not just care about wireless sensing, but also think about wireless actuation. And before I define what that is, my research lab called the YTech lab does all sorts of things wireless, ranging from low power systems to high power, from location tracking to wireless sensing as well. But for this talk, I'm going to talk about wireless actuation. So the place where you might have heard the term actuation is the classic cyber physical systems loop. That is, imagine you have a Nest thermostat at home that's sensing temperature, and then it actually controls the temperature of the room by turning on your AC or your heater. And so that's what we call actuation. Sensing is just perceiving your environment. Actuation is actually controlling your environment. And often these go hand in hand. Now, you've heard a ton of amazing talks about wireless sensing, which is using, let's say, wireless imaging with a millimeter wave radar, for example, or underwater to perceive the environment, say on a drone and so on. That's cool, but what could we do if you wanted to do something called wireless actuation, which is, can we use RF and wireless systems in general to influence our environment, not just perceive it? So I'm just going to dive in and show you an example. So this is our system called software-defined cooking. And the idea is uses something fairly familiar, which is, if you haven't recognized what's on the screen already, it's a microwave oven. Now, this is a 50-year-old concept of just using RF energy to heat, specifically heat food and cook. So what you see there inside the microwave oven is just different blinking lights that show you how different parts of the microwave oven are heated. So here, this is actually RF influencing the environment. It's, of course, the environment within that chamber. But if you think about what today's microwave oven looks like, it's fairly primitive. It's a blunt heating device. So if you've ever heated food in a microwave oven, you're probably not happy with the hot spots or the cold spots that you get when you're reheating your pizza. And you're not really thinking of it as a cooking device per se, even though it's technically cooking. It's more considered a reheating device, primarily because of this uneven and unpredictable heating. So can we do something better than just blind heating, which is what the microwave oven does today? And so this is where the control loop comes in. What if we could sense what the microwave oven is doing, which is this classical wireless sensing, and then actuate it, which is control it a lot better in how it heats the environment within that Faraday cage. So let me talk about what we do for sensing first. Now, you might say, okay, let's just put sensors in there, a temperature sensor in there in the microwave oven. So I have this dramatic video in there to show what happens if you put anything metallic inside a microwave oven. So if you ever tried to heat something with aluminum foil inside the microwave oven, please don't, because this is what can happen, and basically metal sparks. The other approach is to just place a thermal camera outside, which is possible. You're limited by the resolution. But the main challenge there, of course, is that this measures heating after the fact when we actually want to measure the electric field in real time, which becomes a little more challenging. And so what we do is I kind of spoiled it with that picture earlier, is use neon lights as wireless sensing energy harvesters, right? So effectively, they harvest energy and convert it into visible signals, which is what you saw with those blinking lights. So if you remember this picture that I showed you earlier with a bunch of these neon lights that are blinking around, what that is tracking is actually the electric field inside the oven. So there are some spots where the energy adds up constructively, some spots destructively, and that's really why you get food heated out that has hot spots or cold spots. So there's a lot of work that goes on to figuring out how to place these neon lights, as well as how to tune them so that they respond correctly to the wavelength. I'm really going to skip all of that. Now, the next question that you have is actuation. How do you actually control the system so that wireless heating or a wireless actuation is applied effectively. And so if you think about it, there is actually an actuator inside the microwave oven. That's the turntable. So you're currently effectively doing that because you want to heat the food uniformly. That's why the turntable exists. But here's a picture on the right to show you that that doesn't quite work the way that you want. So on the top right, you have wet thermal paper, and you see the black spots where there's high energy. And you see that without the turntable versus with the turntable, what you're really getting is these hot spots smeared around rather than the uniform heating that you really want from a microwave oven. And so what we instead do is have this programmable motor, programmed by very simple Arduino, that effectively moves around this microwave oven with a few pre-programmed, well-designed hot spots and cold spots that effectively improves how that heating is achieved. And so this is the result, just to show you a teaser of how this looks. On the top, you have the pictures with the no turntable, and on the bottom left, you have uniform heating. Actually, the fact that there's not too much black there shows you that there is actually, the heat is relatively uniformly distributed, and we can actually do more interesting heat fabrication. So this was a paper at Mobicom, and that's why you see Mobicom sort of printed over there. So those portions were heated, but you can also heat different types of food. So this is rice with some pink pigment that sort of shows you how different parts are heated. And so at the bottom there, we have the rice heated uniformly. We also have cooked meat and all sorts of other things in the oven too. But I wanted to close with posing another question, which is there more to wireless actuation than just cooking? So I presented this grand concept at the beginning, but can we do much more than just heating some food in the microwave? But there are also some other interesting things you can heat. So this is one of our more recent projects on bringing wireless heating to soft robotics. Specifically, these are robots that change shape when heat is applied. So imagine the kind of origami robots that you see with robots sort of changing shape when you apply heat. Typically, this heat is applied with a heat gun or a laser, but then that needs to be in contact or in very close line of sight. What if this is a robot navigating a pipe? So we effectively built this system called WASER, which is wireless actuation for soft robotics, where we could make these robots bend. We could make the robots to all sorts of different interesting shapes, like, for example, folding as well, by just applying wireless heating. And the reason these pictures are hazy is because they're inside pipes, just plastic, clear plastic pipes. We can also make robots navigate through confined spaces like, say, pipes, effectively by applying external heat to a microwave, and we'll sort of play ahead and show this robot sort of crawling as you sort of heat this liquid metal that's running in this line there that you see. And so you can make all sorts of interesting geometries. So we've since then built hopping robots and climbing robots and all sorts of other robotic platforms as well. So what's next for wireless actuation? So I don't want you to fall with the illusion and the impression that actuation is all about just heating. You could think of classical wireless power transfer and energy transfer as also a form of actuation. You're effectively transferring energy to the device. So wouldn't it be cool if your wireless infrastructure could transfer energy in addition to communicating and sensing, right? There are also a lot of health applications where RF is used not just to sense, like radar-esque, but also to as a treatment plan. And so there's obviously new directions for wireless actuation for health. And last, to conclude, I know Joerg started with this vision of joint communication and sensing, and he had the acronym on his slides, JCAS. So to close the loop, I'm going to make the case that A in the ACS should not be and, that's too boring. It should be actuation. And so with that, I conclude. Thank you so much, and hopefully, pass the baton back to Lili to start the panel.
Thank you, Swarum. It's very cool to see wireless actuation for microwave and soft robots and many things that we could potentially imagine. And looking at the Q&A, we have all the questions answered. So let me quickly conclude. Thank Matt for the great opportunity for sharing the wireless sensing with the community. And thank all the speakers for sharing their amazing research. It really opens my eyes. And also thank everyone for attending. And the next session, we will have, let me see. So the next networking channel session will be on September 18th. So see you in 4 months. Thank everyone. Bye-bye.